Thank you for being part of part 2 of lecture number 9. This time we're covering linear dependence and independence. We're going to be looking at, we have here set in vectors is linear dependence. Different sets as you use them in sets A, B, C, D. If some linear combinations of those vectors is 0. So if you have A plus B minus C equals 0, any combination will work. And then it will say that it's linear dependent. Okay? As we have here an example, when we're talking about linear independence. When we talk about linear independence, just want to go over just a little more detail of linear dependency and independency. When two vectors, like I and j, are linearly independent because there is no number, a or b, as long as it's not 0, such that the linear combination ai plus bj is 0. In general, a set of vectors is linearly dependent if some linear combination of them is 0. So that's what we have up to ABC equals 0. And here we also have, as you can see here, we have, we rearranged this and we got this to 0 using reduction. So this one falls back, and what do we have to look at to determine if it's linear dependent or not dependent? We have to, in general, vectors are linearly independent because there is no number such that when it's multiplied or added or subtracted to any linear combination, it does not equal 0. And it's just the exact opposite on the other end. It has to equal 0. Now we're also talking about homogeneous equations. We've talked about homogeneous equations and differential equations before, but let's understand a little more. Okay, when we talk about homogeneous equations, we should consider sets of linear equations. Here we want to consider the special cases of such equations when the constants on the right hand side are 0, or where it equals y, because they have the form ax equals y. These are called homogeneous equations. Okay, as we can see here, we have all of the what? Everything equal to 0. And so this would be considered a homogeneous equation. When writing homogeneous equations corresponding to what we have here on the board, together with some reduction, we started with this and we're going to go to this as a reduction. And as we have this one here, it's a different set. And as you can see, we're going to go to reduction again. Okay, and as you can see, we have all these at 0. But remember, this is a combination of this. If this is a combination of this, these are parallel. So that's why everything is practically equal to 0. This is not. Okay, we fool around with the determinants again. Okay, determinants of coefficients. If the determinant equals 0, then the matrix is singular. Okay, and if it's singular, you can't find the inverse of it, because 1 over 0 over the determinant you cannot do. Okay, now if you have one where the determinant is not equal to 0, okay, then you can move forward in your calculations. So what we're going to do is we're looking at this theorem here, and this is the example we're going to use. Well, basically what this theorem says that what we're trying to do is trying to find out how can we solve for our solutions. When we have an issue, or how can we determine, depending on how many, what do we call them, how many equations we have, okay? And so using this technique, this theorem here, this theorem says we shall be particularly interested in knowing that a given set of function is linearly independent. For this purpose, the following theorem is useful. If f at x, f2 at x, f3 of x, and all the way have derivatives of order minus n, or n minus 1, and if the determinant is not equal to 0, determinant is not equal to 0, so it is a linearly dependent. Okay, let's look at an example here. Okay, and so what we're going to do is we are given this as our variables, okay, and then what we have to do is take the derivative. Okay, so if we take the derivative of x, we get 1. If we take the derivative of e to the x, we get e to the x. And so this goes in the first column, okay, the first row, and then the derivatives goes in the second row. And then we take the determinant of this. Okay, the determinant, when we multiply x times ex, we get x times ex. When we multiply 1 times ex, we get minus e to the x. Now this is not 0, so this means that this is linear dependent. Okay, so let's try another problem. Okay, let's look at this particular set of variables. Okay, so if we look at this, we take the derivative of x, we get 1. We take the derivative of 2x, we get 2. Okay, so now we have to set it up so that we can see if what the determinant is. As we said, we take the original set of numbers or set of functions, and they put in the first row, and the derivatives in the second row. And if you have 3 of them, then you have to take 2 more derivatives. It just keeps on going depending on up to n. And so if we multiply x times 2x, 2 by 2, you get 2x. You multiply 1 times 2x, you get a minus 2x. So 2x minus 2x is 0. So this says this determinant is 0. It is singular, and it is linearly dependent. Okay, so with that, we would like for you to work this problem. We just went through some. We just went through 2 examples. One that was linear dependent and one that was not. And this question says, please determine whether the systems of equation has any solution other than a trivial solution. It's a trivial solution if everything over here is 0, which it is. Okay, so try at it and get back with me. Thank you.